2. Okay. I want to mention something about the labs, and in particular about finding the slope of the best fit line. Now I'm looking at the labs now, starting to grade them. I'll be a little bit more lenient on these first 1 or 2 because, you know, I haven't had a chance to give you feedback. But what I have seen by several people is a hyenas, no, 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 you do not do that. And that is when you are drawing your best fit line, for instance, if you have V here and T here, seconds, say centimeters per second, and every graph should have a title and units and coordinates and so forth. So you've got some, actually it's going to be easier to cheat and draw the straight line. And in these labs I have given you, is that a straight line? No, it's not. Okay. You of course use a ruler to draw that line. You do much, much better than I do. But ultimately you're going to have points here, and you need to circle those data points, but you do not have to label them. You don't have to label the coordinates of those points. Those are in the table that you've got, right? But what you've done is you have drawn with a single stroke a line that best fits those. And as I always explain, think of these as pylons out in the ocean, and you're taking a piece of roadway that's been prefabbed and you're airlifting it down, and you're going to set it on these pylons, and you're going to try and balance it best as possible. That's probably the best way to describe it. And once you've done that, the center line down the road is the best fit line. Then you have to determine the slope of the line you drew, and therein lies the problem. Some of you did not calculate the slope of the line you drew. Some of you used a couple of the data points and drew a line through those too. Or you used the data points as the slope points. Thou shalt not do that. Even if the data point does lie on the line, technically it probably doesn't lie exactly on the line, and so you must not use data points to calculate the slope. If you chose, say, this point and this point as data points, you're actually calculating the slope of the line that connects those 2 points, not the slope of the line that you drew. And those are 2 different things. So you have to choose points, not data points. And they should be as far apart as you can comfortably make them. They shouldn't be like this. And once you have chosen them, you can always, well, in choosing them, you can choose those you can choose those slope points so that you can always read at least one of the coordinates exactly. The slope point that you choose can lie on a horizontal line or a vertical line. And then you know that coordinate exactly. Then you have to estimate or interpolate the other one. It's very unlikely that a slope point can be found that lies right on an intersection of a vertical and a horizontal line. So you can choose one, for instance, if you've got something like this, and the line goes like that. That's a good one to choose because you can read this vertical coordinate exactly and the or horizontal coordinate exactly. The vertical coordinate is just about exactly halfway in between these 2, and that makes it easy to estimate what that is. So you can choose them, and already I have seen in most cases when people wind up with a bad value for their slope, it actually isn't usually the fact that you've drawn the line poorly. People seem to be able to do that. Use a clear, see-through ruler. Don't use an opaque ruler. You have to have a see-through ruler so you can see through it to see how it nicely skims in between all of them. So use a see-through clear ruler when you draw your best fit line. But when you read the coordinates of this, this is where mistakes are made. I've already seen where people misinterpret this, misinterpolate it, and then they get a 10%, 12% error because they misread the slope point. That's where the mistakes are usually made. But the key thing is, do not use data points for slope points. To do that is to essentially ignore the line that you drew. So why'd you even bother to draw it? Yes, sir?
Do you want us to put the coordinates of the...
Yes, I want this. Once you have this here, I want to have the coordinates of that here, and I want to have it there and with units. Why do I want that? Because, as I said, I've been looking through these and grading the questions and stuff, and I've been going through and looking at them, and I can see for one person that this coordinate was read incorrectly. When I can see what it was, what they thought it was, and look over here and see what it actually is, I go, up, there's the mistake. You need to have practice in reading graphs accurately. Okay? Any questions there? Any questions? Also, since I'm talking about this and talking about graphs, this is a velocity versus time graph. One of the homework problems, which was 2-58, I can talk about it now, was a graph that looked like this, right? I think it was number 58. And the question was, is there any place, this is, we got to be careful here. This is position and this is time. And the question was, are there any places where the velocity is constant? The answer is yes. From about here to here, whatever this time was, something like 0 to about 18 seconds, the line is essentially straight. So it's going at constant velocity here. And then the question was, where was it moving fastest? Well, that's right there. Wherever it was steepest, whatever that was, I think it was 27 seconds or something like that, 27 and a half seconds. Right around here, it's going fastest. The question was, is there any place where the velocity is 0? The answer is yes. Right up at the tippy top, at about 37 and a half seconds, the slope is 0, if only momentarily. And then the last question was, does it go one direction or does it go both directions? What's the answer? Both. It's going sloping up here, that's forward. It's sloping down here, that's backwards. It went both directions. It was moving forward at constant velocity. It accelerated and sped up. It slowed down, turned around, started going backwards, and then came back through. And yes, I'll probably have something like this on the exam as a multiple choice question. So, and I've got this posted, I've got this solution posted. Any other questions or comments? So where were we? The football problem? We were doing the football problem. And which essentially is the key feature of the football problem is that the ball returns to the same height. So in this case, we're told that a ball is kicked from the ground at some initial velocity. We know what a football does. It comes back down. This is y, this is x. And we were told the initial velocity. And the initial velocity was 20 meters a second, 37 degrees up. So we were told this was 37 degrees, and this was going 20 meters per second. And what we found was this, that the initial x component was, I believe, 16 meters per second, and the initial y component of velocity was 12 meters per second. And what I did, even though I didn't draw this correctly, will later prove that this is actually a parabola and is symmetrical. And one of the things that I showed was that it hits at exactly the same angle. I proved that. That what happens to this, here it is, the y component. The y component is going up and then it's coming back down. And if we draw the initial velocity in a vector diagram, it was, we had, let's see, 16, and then we determined that this was 12. So we determined the components of the initial velocity, that the horizontal component was 16, the vertical component was 12, and that's consistent with this being 37 degrees and this being 20 meters per second. Now I will reiterate, when I draw my vector diagrams like that, I always label the triangles with positive numbers, because that's the length of the side of the triangle. The component might be negative, but I label these trigonometric diagrams with the length of the sides. Now what I showed was that V final was like this. That this part of it, the horizontal part, did not change. There's no acceleration horizontally, so it always goes 16 meters a second horizontally the entire time. Meanwhile, it's going upwards at 12 meters a second, and then it comes down, and I proved that when it comes back down in vertical motion, that the speed is going to be the same, but it's going to have reverse direction. Now, if you look at that, given these angles, you can then show that this angle has to still be 37 degrees, which means this is 37 degrees. So if it's kicked upwards at 37 degrees, when it comes in and strikes the ground, the angle that it comes in and strikes the ground at is also 37 degrees. What can you say about its final speed? How do you calculate the final speed? How do you calculate the magnitude of that vector? Whose theorem? Pythagorean theorem. But look at it. 12, 16, 12, 16. This is obviously, just by inspection, it's 20 meters per second. When it strikes the ground at the same height it was kicked, it hits at the same speed it was kicked, at the same angle that it was kicked. So when it plows in here like that, if I took a tube and adjusted it to 37 degrees, that football would come straight right in. Boom. Right in there. But that's only if the initial and final heights are the same. That's what makes this simply reverse. Here it's up, and then here it's down. Now the questions we can ask are things like, how high can it get? How far did it go? And how long was it in the air? Those are the kind of questions we can ask. Okay? How high did it get? How long was it in the air? Okay? How far was it kicked? How long in the air? Well, let's take a look at how high. Let's look at how high. Let's call this Y final. Okay? What you look at here, I'm going to redraw the problem. The horizontal motion does not change the situation. The fact that it's moving 16 meters a second sideways does not affect the vertical motion. But initially, it's going 12 meters per second vertically, not 20. Vertically, it's this part. This is the part that affects the vertical motion. It's going upwards initially at 12 meters a second. So you go back to chapter 2. A ball is projected upwards at 12 meters a second. And since this is plus, I'm using this sign convention. So what is A sub y with that sign convention? This is the kind of thing you must do. Since it's only under the influence of gravity, what's the magnitude of the acceleration? That shouldn't be hard at all. It's g, right? But is the y component of the acceleration plus or minus? If upwards is plus, what's the direction of the acceleration due to gravity? It's downwards. Don't say minus. It's downwards. In some problems, we might say down is plus, and then you're in trouble. But in this case, the y acceleration is minus 9.8 meters per second squared. And so I can say that, how high does it get? Well, if you write down the constant acceleration equations, those 4 equations, and by the way, I'll probably send it out to you, but I'll also have to distribute it here. I'll have an equation sheet which shows all the equations you need to know how to use to do the exam. And you'll have that attached to the exam when you get the exam. You'll find out it really doesn't help that much. Because it's not knowing the equation, it's knowing what the hell to do with it. But if you look at those constant acceleration equations with the y in place of the x, you find this, that v final y squared is equal to v initial y squared plus 2a sub y delta y. That's the same as vf squared equals vi squared plus 2a delta x. But we have to put in y subscripts because now we've got a two-dimensional problem. What is vfy final? What is the final velocity at the top, people? Quick, quick, what is it? At the top, what does it do? It stops. So what's v final y? 0. This, in this case, is 0. Solving for delta y. Solve for delta y first before you go and plug numbers in. Don't start plugging numbers in at this point. Do the algebra first. Bring negative, I get negative v initial y squared, and then I can divide by 2 and a sub y, and I get delta y. I skipped a few algebra steps. Don't you do it. You show those steps, okay? So that negative v initial y squared over 2ay is delta y. And delta y is y final minus y initial, but y initial is 0. So this is the same as y final. We put our coordinate system right here. So y initial is 0. X initial is 0. So we plug and shove. Negative. And then we've got 12 meters per second And don't make the mistake, the negative sign is not included in the squaring process. It is not included, it's outside of that. And what is a sub y? Negative 9.8. Notice I put this in parentheses so it's not 2 minus 9.8, it's 2 times negative 9.8. And then we have seconds squared per meter because we reciprocate and multiply units when we divide by units. Notice you're going to get seconds squared, we'll cancel seconds squared. Meters go into meters squared, meters. And negative divided by negative is positive. We're going to get a positive answer. That's good. And you can grab your calculators and calculate this, okay? Let's do it. Let's do it. So it's 12 squared divided by parentheses 2 times 9.8 close parentheses, is 7 point, did they actually calculate this here? I don't think they actually, yeah, 7.35 meters. So there's how high it gets. So we just figured this out, okay? Anybody else get that? Don't trust me. Wish you could see me smile. It's Sydney, right? Yeah, I wish you could see me smile. He said, but you know what? People have told me I look better with the mask. Now that's depressing. But, you know, okay? So we found this out. All right. Can anybody see, how can we figure out the time? How can we figure out the time? Well, there's a really hard way and there's a really easy way. Okay? One thing you can do is use x final, you can use a quadratic equation. No. Okay? But let us look at this situation. Since we have this answer. Now, can I take this off? Can I take this off? Okay. See, once you get one answer, you can go get another one. An object is thrown upwards, not at 20 meters a second, but at 12 meters a second. Okay? How long does it take to get up to the top? See? Find out how long it takes to get up to the top, because didn't we prove that if you throw an object upwards and it returns to its original position, that the time for it to go up is the same as the time to fall back down. If we can find the time for it to go up and double it, that's how long it's in the air. So an object is thrown up. Let's take a look at this one. How long? How long? Well, same problem. It's thrown upwards, not at 20. You must use the vertical component of the velocity. This piece of the velocity. An object is thrown up at 12 meters a second. How long till it gets to the top? What is the initial, what's the final velocity at the top again? 0. Okay. V final is 0. This is V initial. Whether you put the y's on it or not, that doesn't make any difference. What is the y acceleration? It's, again, minus 9.8 meters per second squared. Well, if I wrote out those constant acceleration equations, one of them that comes out is V final y is v initial y plus a sub y times the time. I know the final y velocity, I know the initial y velocity, I know the y acceleration, I can find the time. This is 0, so I get minus v initial y over a sub y is the time, and that is negative 12 meters per second divided by negative 9.8 seconds squared per meter. I reciprocate the units here and multiply. Meters cancel. One of the seconds cancel. I get seconds. Take 12, and what happens to the negative signs? Cancel, cancel. And take 12 divided by 9.8. I got 1.22 seconds. Anybody else get that? That's the time to go up. Anybody else get that? Yes? No? Okay. Be sure to say, yeah, don't trust me, it's late, I'm tired. Okay. So how long is the ball up in the air total? How long does it take until it hits over here? What do I do to that time? Yes, ma'am. Double it. Since T up equals T down, T total is 2 times the time up, and that's 2 times 1.22 seconds. That's 2.44 seconds. That is the total time. See? That's it. We use the vertical motion to figure out half the time. And so we doubled that to get the time for the horizontal motion, for the whole thing, up and down. All right, who sees it? So there's the time it's up, and here's how long. How high? 7.35 meters. For how long? 2.44 seconds. All right. How do we figure out? I'm going to take this off now. Use this spot. How do we figure out how far it went? Who sees it? It was in the air for 2.44 seconds, and during that time it was moving horizontally at 16 meters a second. So how far did it go? We know that x final is x initial plus v sub x times t. If you go to those constant acceleration equations, what you get is the acceleration is 0, and that's what you get. So x final, x initial 0. So the final x position is 16 meters a second. You use this piece of the velocity. You don't use the 20, you use the horizontal component. So it's 16 meters a second times 2.44 seconds. Seconds cancel. And 16 times 2.44 turns out to be 39.2 meters. See? The time is the thing that's common to both. You treat the vertical motion as if it was a chapter 2 problem, but you must use the y component of the initial velocity. You must use this, not the 20 meters per second. You can't do that, okay? All right? Questions or comments? Questions or comments? And include units. Units all the way through. Now, let me ask this. This also. This will throw people. This is not here. This is a giant canyon. And Evel Knievel takes off at 37 degrees at 20 meters a second and hits over here. How far did he go? Does the fact that there's a canyon in between change any of this? No. As long as he hits at the same height on the other side of the canyon. What if there was a hill in here? Would that change anything either? Well, as long as, we got to be careful that it only doesn't hit the hill. But jumping over a cavern is a hell of a lot easier than jumping over a small hill, because you could hit the hill accidentally. You're not going to suddenly jump down and hit the bottom of the canyon. So if you say an object goes across a canyon, it's just a football problem. As long as the initial height and final height are the same, it's the football problem. No change. Same exact problem, okay? Now, one of the most important and most often asked questions is, what is the range? If this were a gun at sea, I'm currently watching a special called Victory at Sea, which is a history of World War II. It's 28 television programs, a half an hour long. It's some of the finest documentary ever made. Real pictures from all points of view about the sea. When you fire from a ship at sea to a ship at sea, as far as we're concerned, the initial and final heights are the same. The ocean is not tilted, okay? At least not last time I checked, okay? So a very common thing is that a gunner knows the muzzle velocity. They know that with a particular projectile, and if they use 3 bags of powder, that this is the muzzle velocity. So they know what this is. It's not 20 meters a second, it's hundreds of meters a second. But the question is, what angle do I angle this such that I hit the ship? Now they have to know the range to the ship. Okay? Or another question would be, what is the range if I angle this at a certain angle, how far will it go? Well, you can do this entire problem with algebra. We're not going to do that. But if you do this with algebra, you come up with a standard equation that you'll see in ballistics manuals called the range equation. And the range equation is the following. They've got it here. That the range is V naught squared, or range is V naught squared sine 2 theta all divided by G. Now you don't have to memorize that. You could also write whether it's V naught or V initial, okay? This is what we call V naught. Okay? V naught squared sine 2 theta over G. Now notice, if I give you any 3 of these, or 2 of them, if I give you the angle and V naught, you can find the range. If I give you the range and V naught, you can solve for the angle. But then you have to use the inverse sine function. Well, let's just use this just to see if this works. In this case, let's calculate the range. This case, let's do this one right here. What do we get? 39.2 meters. Let's see if it works. Okay. The range in this case, using that equation, is 20 meters per second. Now watch how I do this. All squared, people, times the sine of 2 times 37 degrees all over, and what does the symbol G, what is the sign of the symbol G? Always positive. The symbol G is always positive. It is the magnitude of the acceleration due to gravity, 9.8 seconds squared per meter, because we're dividing by units. Notice seconds squared cancel seconds squared. Meters go into meters squared meters. And here's how you do it. Get your calculators, okay? What you do is, what I do is I go 2 times 37 is 74 degrees. And on my calculator, I just take the sine. And then times 20 and square that and divide it by 9.8. And I'll be damned, I get 39.2 meters. Figure out how to do this on your calculator. Figure out how to do the sine of 2 theta on your calculator. Let us stop there and let's do the quiz. I'll put the homework problems here that I need to assign here on the board. Let's see, what was the last one that I had assigned? You pass them out there. 8 and 9, right?
Yeah.
Okay, I did not assign 18 and 20? I did. What about 22 and 24? Okay, 22, 24, and 27. 22, 24, 27 in chapter 3. For you folks will be due, what is today? Next Monday, I guess, huh? Right? And also, the people on video, since the test is coming up on, they'll be due on Wednesday when you come in to take the exam for the group on video, okay? So I said, so we've got 18 and 20 out there already, and then 22, 24, and 27. Okay, that's good.